Hi, everybody. Today's lesson is for Monday, April 6th. Just wanted to say hello. I hope you all had a great weekend, but let's go ahead and get to the notes. All right, so a couple things admin-wise. Exam 2, again, I'm pre-recording this lesson. Hopefully this will give me time over the weekend to really crank out a lot of feedback on those exams, and hopefully either today, Monday, or Wednesday, you guys will be hearing back from me. I'm a little bit bummed that it was an online exam. Without giving away too much information about my age, I'll share with you that my birthday is tomorrow, and my husband actually got me these stamps that give feedback on the exam, such as excellence, and I was really excited to try them out. But at any rate, that'll have to wait until next year in coastal engineering and capstone. Other news, homework 8 is officially assigned. It will be assigned on Wednesday, April 8th. I put the word officially in quotation. You just couldn't see me because the camera's focused on the page, but all of the problems on homework 8 are optional. Really just consider it practice for the final, sort of also checking in, seeing how everyone's doing. And I'd also like to propose not assigning an in-class 8. Our in-classes are sort of still out of class since we're in this asynchronous video lesson style classes. And another reason I'd like to propose that is because Wednesday I'll also be assigning project 1. I'll give you more details on Wednesday, but that'll be due probably the following Friday. So a little bit more time to work on that. I think we'll be working in teams of 2 or 3, but more details to come on Wednesday. So let me know if you really want to do in class 8. I can definitely, assign a problem for additional practice, things like that. Last time we calculated the drag force due to wind before sort of shifting gears and talking about wave properties. Today, I'd like to talk about how we estimate wave forces on offshore piles, specifically using the Morison equation. And then also sort of, with these waves that are a function of the wave period, time, as well as space where you are, so X, how that can affect how the wave force varies as well. So I think, again, you've probably talked a lot about this in your EN 475 class, but we'll touch on it here as well and sort of talk about how we can use that then in our design and analysis of offshore structures. So let's go ahead and get started. Going along with our outline format, I think this is big letter C, wave forces on piles. And the big equation to know here is the Morison equation. And the Morison equation is a semi-empirical, which means partially based on experiments, but also partially rooted in linear wave theory, equation that's used to estimate the force per unit length of a pile. And so if I write that in equation form, what that looks like is that my total force per unit length, lowercase f sub x, is equal to the combination of my drag force per unit length plus my inertial force per unit length. So again, this f sub x is my total force in units of pound per feet or newtons per meter. F sub d is my drag force, and F sub I is my inertial force. Again, all of these are in units of pound per foot. And it further breaks down equations to calculate the drag and inertial forces. So my drag force can be calculated by taking 1/2 times the density of water times a drag coefficient times my water velocity, which is the combination of my current and wave velocity, times the absolute value of the water velocity, times my pile diameter, plus a mass coefficient, C sub m, times your water density, times pi d squared over 4, times your wave acceleration in the x direction. So again, this is your drag contribution, and this portion is your inertial. And let's go ahead and formally define these variables. I'll sort of put this equation in a box because it is important. And again, we have rho is our density of water. This, if we're talking salt water, 1.99 slug per foot cubed. Or if we're using metric units, that'll be 1,029 kilograms per meter cubed. That's in salt water. And if we're in fresh water, it's equal to 1.94 slug per foot cubed, or approximately 997 kilograms per meter cubed in fresh water. Since we're going to be a lot of times applying this to the API calculations, we'll be working with English units a lot, so say hello to slugs. C sub d is our drag coefficient. If you look in the API standard, they recommend that you can use a drag coefficient between 0.6. So 0.6 is less than or equal to C sub d, which is less than or equal to 1.0. It's conservative to use 1.0 then, so to max this out. So conservative C sub d is equal to 1.0. Unless you're given explicit information, we've done tons of tests and we know that the drag coefficient is 0.7 or something like that. But 1.0 is a good constant to use. Next we have d is the outer diameter. This would be in units of feet or meters. Careful with units here. If your velocity is in feet per second, you want your diameter to be in units of feet as well. I know we've been using inches a lot in the API checks. The U is your water velocity at the cylinder. And make sure that you consider any effects of a background current. So your U formally is going to be the addition of the wave particle velocity in the x direction, so U sub wave, plus any background current velocity. The units will be in feet per second or meters per second. And just to be thorough for the notes, we have U current is equal to the current velocity, and U wave is equal to the wave particle velocity in the x direction, or sort of with the wave. With the equation that I like, you guys, I'm sure, have used a couple equations on the waves equation sheets. I'll post these in the same folder. Sorry for that getting super blurry. I'll post these in the same folder as the lesson notes. But U, there's 3 equations for U. So this is on linear wave properties, where we have surface elevation, velocity potential, moving down to the horizontal particle velocity. I really like this middle equation with cosh kz plus d over sinh. The reason I like that is because this term is the same as we have for our horizontal acceleration. That's that k sub x. So it makes this calculation a little bit easier, and we'll be using both. So just to get these in the notes, we have u wave is equal to pi h over t times cosh of k times the quantity z plus d divided by sinh, the hyperbolic sine of k times d, times the cosine of k times x minus omega times t. Something just to be conscientious of, make sure that your calculator is in radians when you take this cosine value here. So calc in radian mode. Really important that kx minus omega t is in radians. Okay, moving on, that takes care of all of our components of the drag force. So the new terms we have in calculating the inertial force, C sub m, is equal to your mass inertia coefficient. Note that sometimes this is called C sub I. So if you see C sub I in relationship to something with the Morison equation, that probably refers to your mass inertia coefficient. Again, the API standard recommends to use 1.5 and 2.0 as your bounds for your mass coefficient. So it's conservative again to take the highest value of 2.0. So conservatively use C sub m is equal to 2.0 if you're not given other information. And then our equation for AX, I showed it briefly on the equation sheets, but just for the notes, we can say that our horizontal water particle acceleration due to the wave is equal to 2 pi squared times h divided by t squared times that k sub x is equal to cosh of k times z plus d divided by sinh of k times d times the sine of kx minus omega t. Again, be careful to make sure that your calculator is in radian mode when calculating the value of sine. So this is pretty much our equation. This Morison equation is really the crux of what we'll be working with when calculating the wave force. Let's do a quick example, assuming we already know the wave velocity and the wave acceleration. So this will be number 2 example. Let's say at a given moment, we know the horizontal wave velocity at the still water level is equal to 8 feet per second, and the horizontal acceleration is 5 feet per second. We're also in the presence of a background current, so a current of 2 feet per second flows in the same direction as the wave. We're also told C sub d is equal to 1.0 and C sub m is equal to 2.0. And we want to find the total force per unit length on on a pile in a depth of 80 feet with diameter of 36 inches at the still water level. So we want to find the force per unit length at the still water level of this pile. So let's go ahead and sketch what our problem looks like, just to kind of see what we're working with. So we have our water table, or still water level. Here's the bottom. Doesn't really matter what's going on above the still water level, so our pile might be exposed. We know that there's a current that goes in the same direction as the waves of 2 feet per second. We know that the depth is 80 feet. The pile diameter, capital D, is 36 inches. This is equal to 3 feet. Let's go ahead and just get that in there now. We know that our density of water, let's say we're in salt water, so it's 1.99 slugs per foot cubed. And we also know that this pile is being impacted by waves, and at this particular moment, the wave velocity at the pile is equal to 8 feet per second at the surface, and a sub x is equal to 5 feet per second squared. That should have units of acceleration. So we have all this information. Let's go ahead and plug into the Morison equation. So again, Morison's equation tells us that the total force per unit length at a given depth is equal to our drag force plus our inertial force per unit length at those depths, or 1/2 rho times our drag coefficient times u squared, or u times the absolute value of u, times your diameter, plus C sub m times your density of water times pi times your diameter squared divided by 4 times your water particle acceleration in the x direction. All right, so we're given u wave and a sub x already in this problem statement. So the nice thing is we don't need to actually calculate these values separately using these two longer equations. So let's just go ahead and plug in values. So we have f sub x is equal to 1/2. Rho here is equal to 1.99 slug per foot cubed. C sub d is equal to 1.0. Our water velocity is equal to u wave plus u current. So remember to include both contributions. So we have 8 feet per second plus 2 feet per second. Again, this is u wave plus u current is equal to my water velocity total times the absolute value of that. Let's just do the addition, is equal to 10 feet per second. Times our pile diameter is 3 feet, plus, here's our inertial term. We have 2.0 is our mass inertia coefficient, times 1.99 slug per foot cubed, times pi times our diameter is 3 feet squared, all divided by 4, times our x acceleration, which is 5 feet per second squared. I can go ahead and plug these numbers into my calculator, and I get that my total force, my drag contribution to the total force, is going to equal 298.5. And if I go ahead and check units, I have feet cubed on the bottom. This is going to cancel out with 1 foot here, a foot contribution there, and a foot contribution there. And so then we have per second. So we have slug per second squared, plus my inertial contribution is equal to 140.7 slug per second squared. If I pull out these units, we know that a slug per second squared is the same as writing a slug foot per second squared times 1 over feet. And this I know is a pound. So this is how I get to pounds per feet. So units check out, that's good news. And so then finally I can add those together to get the total force on this pile at the still water level is 439.2 pounds per linear foot of the column. And again, this is at the still water level. All right, so that's one example. Important to note though is, again, we said this is at the still water level. So sort of continuing on with the notes before moving on to a slightly more complex example. Let's put big letter D is our note that the wave force per unit length varies with 3 separate variables. So the first thing is depth. So again, we have this value Z plus D. So the depth I'm at plus the total depth. That comes into my calculations for my velocity and my acceleration. Wave force also varies with time, T. And finally, it varies with where I am spatially, which is sort of related to K times X. So my wavelength times my horizontal position in the water. All right, let's do a second example that sort of talks about this variation in time, but especially in space. So this is example 2. Let's say we have 2 piles and they're in 90 feet of water depth. So this distance here is 90 feet. Here's our water symbol. I have one pile here at x equals 0. We can sort of say x equals 0 anywhere, but let's say that our pile 1 is at x equals 0. Pile 2 is 80 feet away from that. So here's pile 2. X equals 80 feet. And we've got some waves. And we know that for the waves, the wave length is equal to 400 feet. The wave height is equal to 20 feet. Again, we're in a water depth of 90 feet. And we know that there's no current. So U current is equal to 0 feet per second. For our piles, we have a diameter of 6 feet for each pile. C sub D is equal to 1.0. C sub M, our inertial coefficient, is 2.0. And we know that they're at 80 feet spacing. And we also know, I drew it here, but we are also told that the wave crest is at pile 1. So all of these following questions apply for when the wave crest is at pile 1. And we're supposed to find a bunch of different things. First, we're supposed to find the water surface elevation, eta, at pile 1. We're also supposed to find the phase, or omega t, of the wave. We're supposed to find the water surface elevation, eta, at pile 2. We're supposed to find the wave period. And then finally, we're supposed to find 2 things: the force per unit length, F sub x, at the still water level on pile 1. And then the force per unit length at the still water level on pile 2. All right, so let's go ahead and work through each of these calculations. For part A, I know that when the wave crest is at pile 1, this tells me that eta at pile 1 is equal to h over 2 by definition, because that's where the wave crest is, and eta is measured up to the wave crest. So this is equal to 20 feet over 2. So eta at pile 1 is equal to 10 feet. Next, we're supposed to find the phase of the wave. Or omega t. I know that if the wave crest is at pile 1, I can make this assumption about the water surface elevation. So we know that eta at pile 1 is equal to h over 2. But we always hold true our equation for eta. So always, this equation, eta x, a function of x and time, is equal to h over 2 times cosine of k times x minus omega t. So we can go ahead and set this equal to h over 2, since we know that at pile 1, eta is equal to h over 2. We also know that at pile 1, so also at pile 1, we've dictated x to be 0, so x is equal to 0. So we can go ahead and plug that in with x equals 0 at pile 1. And so simplifying this equation, we have h over 2 cosine of negative omega t is equal to h over 2, or we have cosine of negative omega t is equal to 1. Here, again, if you think about your unit circle, cosine of a negative value is meaning you're going clockwise. That's still going to be the same as cosine, so this could be positive or negative. But really, if I'm taking cosine of anything equal to 1, I know that omega t is going to then equal 0, because the cosine of 0 is equal to 1. And that's going to happen every time I go around the unit circle. So every 2 pi radians times whatever integer number of rotations I make. So n is an integer. The simplest way to say this is that my phase omega t is equal to 0, but it's most formal to say sort of this plus or minus 2 pi n for every periodic time we go past 2 pi. Great, so that's the phase of the wave. Let's go ahead and use that to calculate the wave crest at pile 2, where I know that x at pile 2 is equal to 80 feet if x at pile 1 is equal to 0. So if x at pile 1 is 0 and they're at 80-foot spacing, we know that x is 80 feet. And we also know that omega t is equal to 0 from our previous calculations. So let's go ahead and plug in values. We have omega at pile 2 is equal to h over 2 cosine of kx minus omega t, which is equal to 20 feet divided by 2. K is equal to 2 pi over L. We know that our wavelength is 400 feet. So let's just plug all of those values in. So we have 2 pi divided by 400 feet times 80 feet is my x position of pile 2, minus omega t is equal to 0. And I can plug all of this in, and I get that my water surface elevation at pile 2 is equal to 3.09 feet. Cool. Moving right along, the next thing for us to calculate in part D is our wave period. So again, when you are relating really wave period and wave length, the key word is dispersion relation. So let's just go ahead and use the full dispersion relation. So we know that by dispersion, that tells us that omega squared is equal to g times k times the hyperbolic tangent of k times d. Or if I plug in, since I'm given L and I want to find T, we can say that 2 pi quantity squared, sorry, that's squared, all divided by T squared is equal to 2 pi times G over L times the hyperbolic tangent of 2 pi times D over L. Solving for T, this gives me that T is equal to 2 pi L over G hyperbolic tangent of 2 pi D over L. Take into the 1/2 power, taking the square root. So plugging in numbers, we have 2 pi times my wavelength is 400 feet. All divided by gravity in English units is 32.2 feet per second. Times the hyperbolic, sorry, feet per second squared, times the hyperbolic tangent of 2 pi times my water depth is 90 feet, all divided by my wavelength of 400 feet. And then I take the square root of that to get that my wave period is equal to 9.37 seconds. Cool. All right, let's finish up. We just have to calculate now the wave force at the still water level on both pile 1 and pile 2. So for letter E, we're supposed to calculate our wave force per unit length at pile 1, where we have x is equal to 0, and we know our phase omega t is equal to 0 because the wave crest is at pile 1. We're told that in the problem statement. Again, this is going to equal my drag and my inertial force per unit length. Plugging in, we have 1/2 rho times our drag coefficient times u times the absolute value of u times my pile diameter, plus my mass inertia coefficient times the water density pi d squared over 4 times my acceleration. Here again, I can kind of just write out my constants, what I know that my density is equal to 1.99 slug per foot cubed. My drag coefficient is 1.0. My mass coefficient is 2.0. My pile diameter is equal to 6 feet. My water velocity is going to equal u current, which is equal to 0 plus u wave, the x particle velocity under the wave, which is equal to pi times h over t times the hyperbolic cosine cosh of k times z plus d. I know that I'm at the still water level, so z equals 0 at the still water level, divided by the hyperbolic sine of k times d times the cosine of kx minus omega t. Let's go ahead and plug in values. We get that this is equal to pi times 20 feet divided by 9.37 seconds is my wave period, times cosh of 2 pi over 400 feet is k times 90 feet is d, divided by sinh of 2 pi over 400 times 90 times the cosine of k times 0 is going to be 0 since x is equal to 0 minus omega t, which is also 0. And so I know that the cosine of 0 is equal to 1. So I'm just going to take this full value and plugging this into my calculator, I get that u is equal to 7.55 feet per second. Let's go ahead and calculate our acceleration, a sub x, which is equal to 2 pi squared h over t squared, cosh of k times z plus d, divided by sinh of k times z plus d, times the sine of kx minus omega t. Now we can save ourselves some work because we know that kx minus omega t is equal to 0, and the sine of 0 is equal to 0. So this whole thing is going to equal 0 feet per second squared. So my acceleration is going to be 0, and I'm not going to have any contribution due to my inertial force on the pile. Plugging these in then, I have Fx at pile 1 at the still water level is equal to 1/2 times 1.99 slug per foot cubed times my drag coefficient is 1.0 times my water velocity is 7.55 feet per second times the absolute value is 7.55 feet per second times my pile diameter, which is 6 feet. And that whole quantity is my drag force plus 0 is my inertial force contribution. And so I get that Fx on pile 1 is equal to 340.3 pounds per foot at the still water level. Great. All right, guys, almost done. The very last step is to calculate the total force per unit length on pile 2 at the still water level. So this is little letter F, which is F sub x on pile 2. Here we have x is equal to 80 feet due to the spacing of the piles. Again, omega t is equal to 0. And again, this is going to be the contribution of my drag force, 1/2 rho CD u times the absolute value of u times my diameter, plus my inertial force, C sub m rho pi d squared over 4 times my x acceleration under the wave. Again, I have the same value of my water density, same value for my drag and inertial coefficients and my pile diameter. But let's go ahead and recalculate what the water particle velocity and acceleration will be under the wave at pile 2. So we have u wave, which is equal to my u for this case, since the current velocity is 0, is equal to pi times h over t times cosh of k times z is equal to 0 plus d over sinh of kd times cosine of kx minus omega t, and that's equal to 0. Plugging in here, we have pi times 20 feet is my wave height, divided by 9.37 seconds is my wave period, times cosh of k is 2 pi over 400 times 90 feet, divided by sinh of 2 pi over 400 times 90 feet, times the cosine of k times x, which is 2 pi over 400 feet, times x now is 80 feet, minus omega t, my phase is still 0 of the wave. Again, I can crunch these in my calculator, make sure we're in radians, and I get that u wave is equal to 2.33 feet per second. Similarly, I can go ahead and calculate my acceleration. I'm just going to go ahead and use this same equation so we can plug in numbers. So a sub x is equal to 2 pi squared times h is 20 feet divided by t squared is 9.37 seconds, that quantity squared, times cosh of k, which is 2 pi over 400, times z equals 0 plus d is 90 feet, divided by sinh of kd, so 2 pi over 400 times 90, multiplied by the sine of kx, so 2 pi over 400 feet times 80 feet, minus omega t is 0. Again, making sure my calculator is in radian modes, I can calculate a sub x is equal to 4.81 feet per second squared. And so finally, I can plug these in to my Morison equation, and I get that f sub x2 is equal to 1/2 times 1.99 slug per foot cubed times 1.0 times 2.33 feet per second times the absolute value, which is still just 2.33 feet per second, times my pile diameter is 6 feet, plus my mass coefficient 2.0 times 1.99 slug per foot cubed times pi times my pile diameter 6 feet squared over 4 times my x acceleration under the wave, or 4.81 feet per second squared. Plugging these in, I get that my drag force contribution is 32.4 pounds per foot. Add that to my inertial coefficient, which is 541.3 pounds per foot. So for this case, we have the inertial component of the force is really dominating what the total force is. And adding them together, I get that at the still water level, we get f sub x2 on pile 2 is equal to 573.7 pounds per foot at the still water level. All right, guys, I think that pretty much takes us to time today. Next, we're going to talk about how we can take these force per unit lengths and use them to calculate the total force or to estimate the total force using Simpson's rule. So thanks so much. I hope you have a wonderful afternoon, and looking forward to talking soon.